In this video, we're going to algebraically solve the critical points in intervals of increasing, decreasing, and concavity, and mins and maxes for the function x to the fifth minus 5x to the fourth plus 2. So let's start with part I. F of x equals x to the fifth minus 5x to the fourth plus 2. So f prime of x equals 5x to the fourth minus 20x cubed. And we take that, to find critical points, we take the derivative and set it to 0. Now we can do some factoring here to make this a little bit easier to deal with. We can pull out a 5x cubed. That leaves us with x minus 4 equals 0. So 0 and 4 make our derivative 0, so those are going to be our critical points. Now that's all we're asked to do in part 1, but because we're going to be looking at concavity 2, let's find the zeros of our second derivative in this step. So our second derivative is the derivative of our first derivative. So 20x cubed minus 60x squared. Once again, we'll set that to 0. And we can do some factoring again. We can pull out a 20x squared, and we get left with x minus 3. So the zeros of our second derivative are 0 and 3. Now let's go on to part 2, finding intervals of increasing and decreasing, and concavity. So for these, I like to use number lines. So this will be my number line for the first derivative, and I put my critical points on there, 0 and 4. And then we can essentially use test points to see if the first derivative is positive or negative in these intervals. So for instance, over here we could use negative 1. Negative 1 cubed is negative. Negative in this term would be negative, and negative times a negative is a positive. And we could use a test point of 1 here. Putting in 1 would be positive. Here putting in 1 would be negative. A positive times a negative is negative. And same thing here if we put in 5, positive, positive, positive. So we've got increasing, decreasing, increasing. So let's write these up in interval notation. The function is increasing from negative infinity to 0 and 4 to infinity. And decreasing in between there. So our interval for decreasing would be from 0 to 4. For intervals of concavity, we'll do the same thing, except we'll do it for the second derivative. So we'll make a number line and put on our zeros. We had 0 and 3. Now our test points will go here in the second derivative. Now, because x is squared here, and whether I put in a negative or positive, it's going to be positive. So if I do negative 1 for my test point, that'll be positive. Negative 1 minus 3 is negative, so that's negative. Could do the same thing with 1. Positive. 1 minus 3 is negative, so negative. So we don't have a sign change at 0, so that's not going to be an inflection point, but it's also going to be neither concave up nor down, so we'll have to reflect that in our interval. If we use a number larger than 3, this becomes positive. As we said, this is always positive. So we got positive. So concave up, well, any place this is positive. Concave down where it's negative. So it's concave up from 3 to infinity. Concave down. Like we said, we have to exclude 0, so it's going to be from negative infinity to 0, and then union that from 0 to 3, and that helps us exclude that 0. Part 3, we want to find the location and value of the relative max, min, and inflection point. Well, we see that the function goes from increasing to decreasing at 0, so we're going to have a relative max at 0 comma, well, this function's easy. If we put in 0, everything zeroes out for the 2 except for the 2. So there's our relative max. We also have a relative min. We can see it from our number line, which is why I like the number line. It makes it very obvious. Decreasing, increasing, there's a relative min at 4 comma. Now we got to put 4 into our function, so for that I'm going to use the calculator, and I want to show you how we can do that in a nice slick way. So I put in the graph as my equation, and I'm going to go to my table set, and I'm going to change that from auto to ask. We bring up our table, second table, we can put in the x values we want to put in. So we put in 4, there's our relative min at negative 254. We're going to need that again because we're going to do our inflection point. We only have one because the sign has to change. This is not an inflection point at 0. In fact, it's a relative max. And so we see we have one here at 3. So we're going to need the output when the input is 3. So let's bring our calculator back up. Enter 3. And the output is negative 160. So that's a nice quick way when we have to find multiple outputs for a function. Okay, we got 2 more parts, and now we're doing the absolute max and min on a closed bounded interval. So by our extreme value theorem, we're guaranteed to have both. Now, all we have to do is check the value of the function at our endpoints of the interval and any critical points that lie in the interval. Remember, our critical points are right here, 0 and 4. Only 0 lies in that interval. So to find out our absolute max and min, we have to check out f of negative 2, f of 1, because those are our endpoints, and f of 0, because that's the only critical point that's in this interval. F of 0 we already know is 2. We can calculate f of negative 2 here, so negative 110. And we can calculate f of 1. And any of these can be done by hand. I'm just showing you how you could use the calculator if you happen to calculate a bunch of different outputs at the same time. So what you get as the smallest is your absolute min, and what you get is the largest, which is 2. Even though that's a small number, is the biggest we got on that closed interval. That's our absolute max. Finally, we got number 5. Notice it's a different interval, so we might have a different min and max. Neither of our critical points are in this interval, so we only have to check f of negative 4 and f of negative 2. And we've already done f of negative 2 here. We know that's negative 110. So we just need to check f of negative 4, and that's negative 2,302. The biggest is our absolute max, and the smallest is our absolute min. Now, for the stuff in blue, we can actually verify all of this from the graph. So let's bring the graph over. So here's the graph in Desmos. And so we said we had a relative max at 0, 2. And we can confirm that right there. 0, 2 is our absolute max. We see it's increasing up to 0. Then from 0 to 4, it's decreasing. Let's pull that up a little so it's on screen. From 0 to 4, it's decreasing down to 4, negative 254. So there's our relative min. And then it's increasing from there on out. So the graph matches what we found algebraically.